Hi, and welcome back to Hacker101. This is the second in a series of 3 sessions on cryptography. If you haven't watched the first yet, I recommend going to check that out first. In this session, we're going to be discussing some interesting practical attacks against crypto in the real world. First, let's talk about stream cipher reuse. If we look back at stream ciphers, we see that they generate a stream of pseudo-random bytes, which are XORed with the plaintext to encrypt data. Anytime you seed the PRNG with a given key, it generates the exact same sequence of bytes. This is why decryption is possible. But consider what happens when you encrypt 2 pieces of data with the same key stream. Each byte of the 2 plaintext sequences get XORed with the same byte from the key stream. Because of this fact, XORing the 2 ciphertexts with each other cancels out the key stream entirely. You end up with the XOR of the 2 plaintext blobs instead. Now, this bug doesn't affect modern stream ciphers like eStream, which take a nonce, or a single-use value like an IV in CBC mode, along with the key. However, eStream is practically never used. RC4 is by far the most commonly used stream cipher, and this absolutely affects RC4. The only mitigation that really helps with this is to XOR the RC4 key with a nonce prior to use. It's not perfect, but it does work. Jumping over to block ciphers, ECB block reordering is one of the nastier bugs you'll run into, and it's surprisingly common. Because each one of the blocks is encrypted separately, there's actually nothing stopping us from arbitrarily reordering those blocks. They're still completely valid in any order or removed entirely. So consider a cookie that contains an admin flag and a username, encrypted with DES in ECB mode. Because DES uses 8-byte blocks, this means we'd encrypt 3 blocks, which you can see on the screen. There's a single byte of padding, which we'll talk about later in the session. If we control our username, there's a big attack we can perform here. We don't need to be able to encrypt or decrypt the data on our own, which necessitates knowing the key, but we can use block reordering to make ourselves an admin. If our username is paddingadmin equals 1 semicolon, we get a block that contains just admin equals 1 semicolon, a perfect replacement for the normal admin equals 0 first block. All we have to do is take that last block and use it to replace the first block. Now we have a valid admin cookie with the username padding. This attack is trivial in most cases and absolutely inherent to ECB mode. Likewise, if we have the ability to decrypt any ECB data, we can use this to decrypt any other ECB data that happens to use the same key. For instance, we could set our username to padding again, then place any ECB block immediately after this. If the username is shown in the web interface, it'll show us the decrypted block. Essentially, if a key is used for more than one thing in an application, it's probably vulnerable to attacks like these. These flaws, and others we'll talk about, rely on the fact that while we may not be able to see the data or even guess the original contents, we can tamper with the ciphertext and the server will decrypt it. The solution to this is really simple. Encrypt your data, then apply a MAC to that. Note that I said apply a MAC to the ciphertext. This is something that many crypto protocols get wrong, but so many things can go badly if you MAC and then encrypt. Always encrypt, then MAC. Now, before we get too much further, we need to talk about one fundamental concept: padding. Given that data encrypted with a block cipher won't always end on a block boundary, we need some way of padding the data to align it properly. Because of this, we always apply a padding scheme, even when we do end on a block boundary. That way we always know what is padding and what is legitimate data. The most common padding scheme in the real world is PKCS7, and it's quite simple. If you need 1 byte of padding, you end with a single byte with a value of 1. If you need 2 bytes with a value of 2, etc. On this slide you can see a couple of samples. Pause and make sure you understand the scheme before you move on. Now, padding has to be validated during decryption. This serves as a basic corruption detection mechanism, and because it needs to be stripped off before use. In PKCS7, you can simply look at the last byte of the last block to see how many padding bytes there are, then walk backwards to make sure they're all there and have the right value. Padding oracles can come into play if you have data encrypted in CBC mode and it's padded with PKCS7. If the server behaves differently when decrypting improperly padded data versus properly padded data, this is an oracle. You can determine whether or not it's padded properly. This may seem like a silly thing to think about, but it gets fun. If you recall from last session, I mentioned that flipping a bit in one CBC ciphertext block will flip a bit in the resulting plaintext of the following block. Due to that, a padding oracle can actually let us use the server to fully decrypt the data without having to know the key. What we'll do is start with the last byte of the second to last block. Modifications to that byte will affect the very last byte. Our goal here is to determine what byte of ciphertext in block n-1 will cause the plaintext of block n to be 1 when XORed together. Once we know this, we know that the plaintext of that byte in block n is ciphertext of n-1 XOR with 1. If we have the data Hacker101 and pad it out to 8-byte blocks and encrypt it, we'll get some ciphertext blob. To decrypt the second block, you decrypt it with your cipher, then XOR it with the ciphertext of the first block. That gets you the original plaintext. With the example, we know that when you decrypt the block feedface 456789AB, you have to get something where the last byte XOR OX23, the last byte of the previous block, is equal to 7, our known padding value. Any other value will cause a padding error, except 1. If the last byte is 1, that's a valid single byte of padding. So if we try all 255 other possible values, we'll know that the other valid one will be the value 1. Once we know this value, we simply XOR that byte with 3 to change the final padding from 1 to 2, and repeat the same thing for the previous byte. One value will be valid, and that value we will know to be 2. By performing this across all the bytes in a block, then walking back from there along the blocks, we can find the plaintext value of every single byte in this data. I cut out a few details for simplicity, but this is the basic process. Google for padding oracle attack and you'll find more in-depth examples and code to execute this attack. As before, macking your data after encryption and validating that MAC before decryption will solve this problem. However, many crypto protocols do not do this and cannot be changed for compatibility reasons. If you can't do this, it's critical that you do not differentiate between errors. It should be a success or a failure. Users shouldn't know why anything crypto-wise is failing. Moving along, hash extension attacks are an interesting case. With Merkle-Domgaard hashes, MD5, SHA-1, and other non-truncated hashes, the digest that you get out is really just the internal state of the algorithm. This leads to an interesting bug. Simplifying slightly, hashes work like this. Initialize the hash, mix each block of data into the hash state, pad the hash, output the internal state. What that means is that you can actually add new data trivially. Put the existing digest into the internal state of the hash algorithm, add new data like you would normally, then pad it accordingly. Now, why is this important? Let's say you have a hash of a secret key plus some data. With length extension, you can add any arbitrary data after the original data without having to know the secret key. Because there's padding between the old and new data though, since it's added by the algorithm, you do need to figure out what that padding is. Then you add the hash padding into the original data. That way the hash still matches when everything is checked out. The process of finding the padding depends on the algorithm. Here you can see some links to resources on exactly that. In terms of mitigation, this is one of the least direct ones, which is to say, you can't actually avoid hash extension attacks if you're using a vulnerable algorithm, period. What you can do is use constructions that sidestep this issue. Think back to HMACs. These used a double hash structure, so you'd have to be able to extend both the outer and inner hashes, which isn't possible. Anytime you're hashing a secret with user data, you need to use an HMAC. In the next and final installment of this series, we're going to be going through some final thoughts and some tips and tricks for crypto in practice. As always, thanks for watching and happy breaking.